So far, we've looked at body parts that are designed to help an organism survive. However, evolution isn't perfect. It can only modify what already existed in a population. So sometimes we can also find traits or small traces of a trait that was once useful but is no longer useful. And those are called vestigial traits. You know how I get all the chicks? It's by doing this. I know, right? I can just go up to somebody and be like, "Hey, sexy," and wiggle my ears a little bit, and they're totally like, "Oh yeah, oh yeah." Okay, thanks.
No.
So if you really want to hit on somebody, the best way to go is probably to wiggle your ears. So kind of like this. Like go like, "Hey there, sexual." Or at least I thought it would work out. I tried it in this dance club the other night, and it didn't really work. So actually, us being able to wiggle our ears is pretty much the most useless thing ever. But in some other species, it's really handy. Like, say, for this fennec fox, for example, this guy has such good hearing that just by being able to change the angle of his ears a little bit, he can actually hear insects digging underneath the soil so he can go dig them up and eat them. Humans also have muscles to move our ears, as I just demonstrated, and you can see them illustrated in this drawing right here. However, those muscles don't increase our fitness in any way. They don't make it more likely for us to get a meal the way it would for a fennec fox. So the way evolutionary biologists have interpreted this is to say this must be a vestigial trait. That is, a vestige or a remains of our evolutionary past. If you go back far enough, probably fennec foxes and humans shared a common ancestor, and that common ancestor benefited from having these ear muscles. But then on one branch of the evolutionary tree, the ear muscles kept growing and becoming stronger and stronger because they helped with survival, whereas in our branch, those muscles weren't making such a difference, and so they've shrunk to these tiny little muscles that barely do anything for us at all. There are plenty of other examples in our body. Take, for example, in koalas, they have this really large structure coming off of their small intestine called a cecum, in which they can digest these eucalyptus leaves, which have lots of toxins in them, so they need this extra pouch to help break down those toxic leaves. However, in the same spot in our digestive tract, you just find this. A tiny shriveled little structure called an appendix. It does nothing to help us digest at all. In fact, from time to time it gets infected and people need to have their appendix taken out by surgery, and it's no good. So it no longer serves any purpose for us. Of course, we're not eating eucalyptus leaves anymore, so it's fine that our cecum has been shrunk to this tiny structure. But that means it would be considered a vestigial trait for us. One last example of vestigial traits would be our coccyx, or tailbone, which you can see right here at the end of our spine. It's just this little series of bones that have been fused together right at the end of our pelvis. This obviously serves no survival purpose for us, but in other species, say in monkeys, tails can make a huge difference in survival, providing an extra limb for monkeys to hold onto branches so they're less likely to fall out of trees and they can more easily reach food that's out on the outermost branches. Now, interestingly, every so often, humans show some of this evolutionary heritage in a different way when they get a particular mutation. So this cute little girl is obviously human. However, due to a mutation that she received, the genes that control tail growth and stop tails from growing in our body was not functional in her, and so her body actually started growing a tail just as our evolutionary ancestors grew tails themselves. And you don't need to wait until babyhood to find evidence for evolution. If you look at embryos, you can see it as well. Just by looking at these drawings of embryos, do you have any clue what they might grow into when they're fully developed? How about now? To me, it's so surprising to think that these species all share such similar early embryos, and it's only later in development that you start to see recognizable differences between, say, turtles and fish and humans. This suggests that all of these vertebrates shared a common ancestor, and likely early in that ancestor's life cycle, their embryos looked like this. It's a commonality that we all share. And then it's only as different genes got turned on in each of these species that it directed the development to be different. in the case of a turtle, to start developing a shell here instead of a dorsal fin, or instead of a plain old backbone like in a human. These embryos would develop or start out so similarly because the genes that direct their development would be similar. And so that's another piece of evidence. If the genes are similar, that suggests that perhaps organisms are closely related. Take this one gene in mice, for example, called PAX6, that directs the development of eyes. It so happens there's a similar gene called eyeless in fruit flies, and another one called the eye control gene in sharks, and the eye control gene in squid, and the eye control gene in flatworms. And look at this. Flatworms, squid, sharks, flies, mice, all of them are so different. But if you look at the actual sequence of nucleotides inside the genes, they're pretty darn similar. Like if you compare a mouse PAX6 gene with a fly eyeless gene, you can find that they are 76.6% identical per letter. Now, with sharks, the percentage is a little bit higher, 85%, and that makes sense because sharks are vertebrates and so are mice, so they probably shared a more recent common ancestor than the mouse did with the fly. But even still, flatworms, which look nothing like mice and don't have a backbone, they're definitely not mammals, they're very unrelated to all these other organisms, still 71% identical. That really suggests that Darwin's idea of common descent was true, because all these organisms are sharing very similar genes with just slight changes. Using these genetic differences, biologists will sketch out how they think different organisms are related, and they don't just have to use DNA. Thanks to the central dogma, they could use proteins as well. In this particular case, they constructed this key looking at a gene for a protein called cytochrome C, and they found that, say, between humans and monkeys, there was only one nucleotide that changed. Whereas between humans and, say, kangaroos, there's 1 plus 7 plus 2 plus 5, so it looks like that's 15 letters that are different. So still not that many letters, but slightly more than monkeys and humans. So they figured, oh, if there's only one letter difference between these two, they must be very related. Whereas if there's 15 differences, that means kind of related, but not quite as closely related. And then obviously there's tons of changes that happen in this protein between bread mold and humans. So bread mold and humans aren't as closely related. The last evidence for natural selection comes from the fact that humans can make their own version of natural selection. When humans do it, it's called artificial selection, not natural, but it functions on the exact same principle. Take, for example, the domesticated dog. At one point, there was a gray wolf, the common ancestor, and some gray wolves started living around humans, and as humans and dogs came to live more and more around each other, humans started to domesticate dogs and started to breed dogs for particular characteristics. So they would choose dogs that had particular traits and cause them to breed together, and that means that the next round of puppies would have more of that particular trait. Now, these aren't traits that helped the organism survive, they're traits that humans liked, like white fluffy fur, or having a cute smushy little face, or having this sleek shape that's good for racing, or having a long nose that's good for hunting, or what have you. But that then shaped the formation of many different breeds of dogs. So the fact that humans could cause evolution by artificial selection suggests that nature, too, could cause evolution to happen by natural selection. So thanks to all of this evidence, the fossils, the biogeography, the homologous structures, the vestigial traits, the embryology, the genetic similarities, and the fact that we can do artificial selection in a way that mimics nature, this is why the vast majority of scientists have reached consensus about evolution, and it's just not much of a debate anymore for them.